Good afternoon, guys. Um, there's one more problem I want to do regarding the vector potential. It's not necessarily in the book in this particular way. It has some subtlety to it, and I just wanted to spend some time and go over some of the subtleties and just end on this problem. So just to remind you, this is E&M fall 2020. We're wrapping up chapter 5, and this will be part 2. So the problem is thus. We're going to have an infinite wire. Okay. I don't really like that wire. I don't know if I can move it, but I'm going to erase it. So notability is kind of fun, but just leave it. Let's just leave it like that. Okay, it looks better. It looks like a human drew it. So it's going to have a current, a steady current, left to right, and it's going to be infinite in extent. Okay, be infinite in extent. Now, what are the questions? Right. Well, the questions are what is A? It's a function of R outside, and what is A sub R inside? Okay. So let's begin to tease this apart. And again, as I said, it has some subtlety to it. So we want to know what the magnetic vector potential is at some distance s away. So let's give ourselves a coordinate system at least, right? So we have z caret. We have s caret, and phi caret will be into the plane of the board. All right. So the typical way one would approach such a problem is, as you recall, is to use the general recipe for the solution of vector potential. You should know where this came from, right? Which is equal to mu naught over 4 pi, the integral of j, which is a function of r primed coordinates, over the volume d tau over r. Now that's a great formula, and we've actually used it, but it's not good in this case, right? So it's not good for currents that extend to infinity, right? So this is not good for currents that extend to infinity. Why? Because the integral diverges, right? So this formula is only good when we have currents which go off to 0 at r equal to or r approaching infinity. So the last problem we did suggests the tactic that we can use on this, right? And so let's begin to do that. I'm going to redraw the wire again. Okay, so here we are, and I'm just going to leave it in human writing. I is in this direction. Okay, and what we want to do is we want to look at, once again, we want to look at the vector potential around some closed loop, okay? We know by Stokes that can be written as so, right? The curl of the vector potential. We know that this is B, and so then this is going to be then B dot dA, and we know that this is a magnetic flux. Okay, so we're going to use all those pieces. All right. So we need a we need a loop here, right? So here's going to be our closed loop. All right. Now a couple of things you ought to remember, right? So you ought to remember that B is equal to mu naught I over 2 pi s phi caret, right? Where s is some distance away from that wire. All right. And where did this come from? This came from Ampere's law. All right. So we know that, which means that through this loop, right, magnetic field is cutting into the plane of the board. Right, we need some distances here. So I'm going to switch up colors. And I'm going to say that this is distance A. Let's say this is distance B. And I'm going to arbitrarily, right, give a unit distance to those two sides. Okay? Arbitrarily give a unit distance to those two sides. So I can calculate the flux, right? That's going to be, it's going to be B dot dA, right? And that's going to be, well, let's first take care of the dot product, right? So we know that that the area vector, right? We're going to make the area vector into the plane of the board. Area vector will be into the plane of the board, which means that B dot A is just going to pick up a cosine of 0 degrees, and cosine of 0 is 1. So then that's just going to be B dot, whoops, B dA. Okay. B then is going to be equal to mu naught I over 2 pi s. All right. It's going to go now, right? How can I calculate the area? Well, this really is going to be S into some space here, which is S plus ds. So the difference between those is going to represent the distance in here. So that's just going to be ds. And so ds times 1 is going to be the differential area. Okay, so this is going to be then 1 times ds will be the area. And we're going to integrate it from A to B. Okay, and so that's going to merely give us, I'll try to get it, squeeze it up in here because I want to try to keep the figure. It's going to be mu 0 I over 2 pi integral ds over s from A to B. That's the natural log, right? So that's going to give us mu 0 I over 2 pi. This is going to be then the natural log of s between A and B, which is going to then be mu 0 times I, 2 pi, This is going to be the natural log of b minus the natural log of a. I can write that as a quotient, but I'm going to leave it this way, and you'll see why in a minute. All right. So that takes care of the the flux part, right? So now let's take a look at the line integral with a, okay? And so that's going to be, it's going to be the following, right? It's going to be the line integral of a dot dl, all right? Now, if the magnetic field at some distance from the wire is the same, right? It's a constant, right? As long as I don't move away from that distance s, magnetic field will be the same, okay? Remember, it's into the plane of the board here, okay? That means that the vector potential along that line must be the same at the distance s as well. It's not a constant, but whatever the vector potential is, it's the same at a distance s away from the wire. And we also know that the vector potential is in the same direction as the current, right? We discussed that in the last problem that we looked at, all right? So if we go around this, this loop of wire, all right, if we go around this loop of wire, then what we want is the following, okay? So let's get a different color going here. So here is the direction that we want to go around this wire, okay? All right. And so now what happens now in this dot product, right? So first of all, the dot product is going to be, right? We know that A is going to be along the direction, right? So at the top, it's going to be in the same direction. DL will be in the same direction as the vector potential. And so then at the top, it's going to be the following, right? It'll be A at A times DL, which is now just a unit length. Okay, so that's going to be times 1. Now down here, okay, down here, right, the vector potential is in this direction, but DL is now 180 degrees from it. And so through the dot product, I'm going to pick up a -1. And so that's going to be then negative A at B times that length, which is 1. So that's going to be A at a distance A minus A at a distance B. All right, beautiful, beautiful. We can scroll down to here. So that, you know, here's the flux. Okay, here's the flux. And remember that, right, got lots of things going on here. That this is equal to the flux, right? This is the key sequence that we need to keep in mind here, all right? So let's rewrite that, right? We have that here. So I like that pink color. I'm going to stay with it for a while. So what we have is this, okay, is equal to the flux, right? And that was the key logic there. And so then this is going to be A at a distance A from the wire, the vector potential at a distance B, and that's going to be equal to mu naught I over 2 pi natural log of b minus mu naught I over 2 pi natural log of a. Now from that, we can say straight off then that clearly, right, this is going to be linked to this, and this is going to be linked to this. So at the end of the day, we can say that A sub R is going to be equal to negative mu naught I over 2 pi natural log of S z caret direction, okay? And this is for outside the wire, for outside the wire. Okay, beautiful. All right. So let me stop there with this little module, and then I'll finish it up in part 2 continued, right? So yeah, this is part 2. And so I'm going to go with part 2 continued. All right, beautiful.